Everyone, welcome to the April 6th and April 7th lecture for Math 302, Differentiating Exponential Functions. Today we're going to discuss exponential functions and the laws of exponents, as well as the derivatives of exponential functions. So the laws of exponents should be somewhat reviewed for you. We'll begin by defining an exponential function. If b larger than 0 is a given number, just any positive number, you define the function that takes an input and sends it to that base, b raised to the x power. This is not to be confused with a power function where the exponent was constant. In the exponential function, the base, b, is constant, and the exponent is once varying. The domain of the function is all real numbers. The range of the function is all positive numbers because this is always larger than 0. In fact, the graph of y is equal to b to the x always lives above the x-axis. We'll see an example of this graph in a second. And also, regardless of what b is, the graph of the exponential function will always pass through the point 0, 1, because b to the 0 is equal to 1 for all positive numbers b. Here's an example of the function 2 to the x. So if x was time and y was population, say of bacteria, this graph would represent a population that was doubling every time interval, every hour, for example. As you can see from this graph, it passes through the point 0, 1. That would represent at time 0 hours, there's 1 bacteria. After 1 hour, there's 2. 2 hours, this is off the graph, but it would be 4. 2 squared is equal to 4. The population bacteria would continue to double. So think of bacteria. Each bacteria is splitting into 2 cells, cell division. Now we're going to review the laws of exponents. To do this, we're going to assume we have 2 positive numbers called a and b. The first law is the product of powers sharing a base. This means we multiply b to the x and b to the y. What we get is equivalent to b to the x plus y. That means we add the 2 powers. The next law is the quotient of powers sharing a base. This means we divide b to the x by b to the y. This is equivalent to subtracting the powers x and y. Then we take the power of power, b to the x, raised to the y power. We get b to the x times y. That's equivalent to multiplying the powers. Next, we change the sign of a power. B to the minus x is the same as 1 over b to the x. That means we're taking the reciprocal of b raised to the x power. Remember, the reciprocal of a number is 1 over that number. So if we change sign, we have to take the reciprocal of 1 over b to the x and then replace this negative with a positive, or equivalently replace the positive with the negative. That's how we change the sign of power. Power of a product, a times b raised to the x power, is equivalent to a to the x times b to the x. That means we raise each power, each factor, a, to the x power, and then b to the x power. Power of a quotient. A over b raised to the x power is equivalent to a raised to the x power divided by b raised to the x power. This means we are raising both the numerator and the denominator to power. Another important property of exponents is that, and this is used especially for equations that involve exponents, equal bases correspond to equal exponents. If b raised to a power is equal to b raised to another power, then those powers, those exponents, have to be the same. And this will be in particular important. You'll see equations that can be reduced to b to the x is equal to b to the y, or b to a constant is equal to b to some function of x. You equate that function of x equal to that constant, and you can solve for x just using algebra. Here are some examples of the laws of exponents in action. 2 cubed times 2 to the 7x is equivalent to 2 to the 3 plus 7x, adding the powers. This is going to be important, especially when we get to the section on differentiating exponential functions. 3 to the 5x over 3 to the 2x is equivalent to 3 to the 5x minus 2x. 5 minus 2 is 3, so we're left with 3 to the 3x. Subtracting the powers. 10 squared to the 7th power is equivalent to 10 to the 2 times 7. That means we multiply the powers. 2 times 7 is 14 in this case. 1 over 5 to the 3x. If we want to change the sign of 5 to the 3x, or equivalently just write this 1 over 5 to the 3x as 5 raised to a power, we notice that this is equivalent to 5 to the negative 3x. A base raised to a negative exponent is equivalent to 1 over the base raised to that exponent. Or equivalently, you could say this is equivalent to 1 over 5, that whole thing, to the minus 3x, and the 1 over doing that twice would cancel out. 14x over 2 to the x, that's equivalent to 14 over 2 raised to the x power. 14 over 2 is 7. 7 raised to the x power. This is a quotient of powers. 5 to the x times 2 to the x is equivalent to 10 to the x, because 5 to the x times 2 to the x is equivalent to 5 times 2, all raised to the x power. 5 times 2, of course, is 10, so we're left with 10 raised to the x power. Here's an example, solving an exponential equation. To solve 3 to the 7x is equal to 81, we follow these steps. Our first step is to write 81 as a power of 3, because we want both sides to be written as 3 to a power, or be written as an exponent where each side has the same base. We rewrite so each side has the same base. 3 to the x equals 3 to the 4th. Now we equate the exponents, and voila, we can solve for x. 7x equals 4. That means that x is 4/7. The slope at 0, 1, and defining the number e. So now we're going to, now that we've reviewed the laws of exponents, we're going to discuss how to differentiate the exponential function. To differentiate the exponential function, notice I said the word the, not a exponential function, we need to define what we mean by the exponential function. The exponential function means the base is e. Well, how do we define e? E is defined, as we'll see, using limits. If the function is b to the x, recall that f prime of 0 is the slope of the tangent line to the function at 0, 1. F prime of 0 is the limit as h goes to 0 of b to the h minus b to the 0 over h. That's the same as the limit as h goes to 0 of b to the h minus 1 over h. This is true for any number b, any positive number. E is defined as the number that satisfies this limit is equal to 1. That means the slope of the tangent line to y is equal to b to the x, or in this case, y is equal to e to the x at x equal to 0, the point 0, 1 is equal to 1. The function y is equal to e to the x has a tangent line with slope 1 at the point 0, 1. Remember, every exponential function has to pass through 0, 1. Now this is how we differentiate e to the x. We let f of x be equal to e to the x, and then we get the derivative is e to the limit as h goes to 0 of e to the x plus h minus e to the x. We use laws of exponents to break this up. If you recall, the sum of exponents is equivalent to product of powers sharing the same base, e to the x times e to the h, minus e to the x. Now factor out e to the x. we're left with e to the x times limit h goes to 0 of e to the h minus 1 over h. This limit is positive 1. E to the x times 1 is equal to 1, so we're left with e to the x. The derivative of f of the x is e to the x is the function itself. If you differentiate e to the x, you get back the original function. So that's pretty cool. We haven't actually seen any functions like that before. And it turns out actually that if you ask the question, which functions have a derivatives equal to the function themselves, what you'll get is the function that is a constant multiple, a times e to the x. Here are some examples. So now that we have another rule of differentiation under our belt, derivative of e to the x is e to the x, we can combine that with the quotient rule and the product rule, and next lecture also the chain rule. Function e to the x over 3 minus x squared, we differentiate that by using the quotient rule. Derivative of e to the x is e to the x, multiply by the denominator, subtract the derivative of the denominator, which is negative 2x. Subtracting negative 2x is equivalent to adding positive 2x, multiply by the numerator, e to the x. Divide by 3 minus x squared. You can take 3 minus x squared to the second power. You get 3 minus x squared squared. H of x is x cubed times e to the x. This is the product of two functions. We now know how to differentiate e to the x, so we're left with the derivative of h of x is 3x squared e to the x plus x cubed e to the x, which is the same as, we can factor out e to the x that appears in both terms, so we're left with 3x squared plus x cubed e to the x. The function g of x is the square root, so this actually is an exponential function combined with the chain rule and quotient rule. We're taking the quotient of a function that includes the exponential function, e to the x, and raising it to the 1/2 power. If you recall from the generalized power rule, derivative of a function raised to the 1/2 power is 1/2 times that function raised to the negative 1/2 power times the derivative of that function. This whole term here, the whole factor here, is the derivative of the function, is the derivative of the outside function, in this case, function raised to the 1/2 power, evaluated at the inside function, left the inside function alone, and this last factor here is the derivative of the inside function, the derivative of e to the x over x plus 3. The derivative of e to the x over x plus 3 is e to the x times x plus 3 minus e to the x. Because the derivative of e to the x is e to the x, we leave the denominator alone, we subtract the numerator, which is e to the x, times the derivative of the denominator. The denominator has derivative equal to 1 because the denominator is x plus 3 and the derivative of x plus 3 is positive 1. So we're left with e to the x times x plus 3 minus e to the x over parentheses x plus 3 squared. This simplifies. You can multiply this out. First term here is x e to the x. Second term is 3 e to the x. Subtract e to the x, we get 2 e to the x. Divide by x plus 3 squared. There's our answer. And next lecture, we'll continue and we'll combine exponential functions with the chain rule to see how to differentiate e to a function. So where we have a function in the exponent, not just e to the x. And we'll also continue by how to differentiate logarithmic functions, and we'll see later on that logarithms are the inverse of exponential functions.